This is CBS Eye on the World. I'm John Batchelor. Asteroids, meteors, comets, the material we swim through on the planet Earth and our solar system. I welcome Greg Brennecka. Greg is the author of the new book, Impact: How Rocks from Space Led to Life, Culture, and Donkey Kong. He is a cosmochemist and a staff scientist at the Lawrence Livermore National Laboratory in California. Right now, however, he's going to travel with me to Normandy, France. The year is 1803, the same year Thomas Jefferson acquired the Louisiana Purchase. And we're going to witness the documentation by a young French scientist named Jean-Baptiste Biot of rocks that fell from heaven, because until this moment, there was doubt where asteroids and meteors and comets came from. Greg, a very good evening to you. Congratulations. What was Biot's mission when he traveled to Normandy, and how did he fulfill the mission so that we can date your work in meteors from that moment? Good evening to you.
Yes, good evening. Thanks a lot for having me. Biot's mission was actually quite simple. It was figure out what happened. And there was a ton of witnesses for this event. It was a big meteor shower with a lot of stones that were recovered. And that was very confusing. And kind of the powers that be wanted to find out exactly what happened. So he was sent to investigate, and that was his charge. And he did a fantastic job of it. And it turned the course of history, at least for meteoritics and our understanding of where rocks falling from the sky come from.
The detail I enjoyed is that he charted where the pieces fell. There's a graphic in your book that's wonderful, showing all this meteor shower hitting the ground. And until that point, even though people were reporting on this routinely, they were always accused of fairy tales and folk tales. He documented where they fell. And you said it formed an ellipse. Is that so? It fell according to mechanics?
Yes, exactly. And when I say he did a thorough job of investigating this, it included maps of where all these reported falls were. He went out and collected samples. He was able to do some scientific investigation on those samples. He did interviews of people from all walks of society, from kind of the upper echelons of society to people that wouldn't necessarily have had the opportunity to be educated. So he interviewed everyone that he could talk to, and everyone was telling basically the same story. And certainly for the time, that was very powerful.
This is the beginning of your profession, Greg. So let's go back to the very beginning that you document, 4000 BCE, which is 6,000 years ago. Iron pieces in a grave in Iran. Why is the fact that it's iron significant? How does that tell us how old it is and how people first understood these things that fell from heaven?
Well, the fact that it's iron is important because humanity didn't have the capability to make kind of native iron as we know it, in that shiny metal, at that point in history. We weren't able to manufacture iron. All the iron that we had at that point came from the sky. So that alone tells us that because someone was being buried with this material, it was looked at as very special, something that fell from the heavens or fell from above. So that in itself is quite powerful.
The iron that fell, they called it black iron it was black rock. And we go to Egypt now. The Egyptians have an hieroglyphic that says iron from the sky. So they were connecting. I'm looking at a crater called Gebel Kamil, a crater there. In South Egypt, did they find pieces of iron around it? Is that why we know about the crater?
Yeah, there's a lot of different speculation as to different meteorites that could have formed that crater. And anytime you have a meteoritic crater that forms like that, there's a chance to find material around it, particularly when it's a robust meteorite like an iron meteorite.
Now, Mesopotamia, Greg's book is filled with these anecdotes. They're compelling. Mesopotamia, it wasn't happy for just finding a piece of iron to make into a dagger. They wanted to interpret it. And the one I liked was, a mighty rebellion will break out into the land. And so they saw the falling of these meteorites as significant in their historical events. That's similar to how comets in the Well, the last 1,000 years were interpreted as augurs of either the birth of kings, the death of kings, or the four horsemen riding.
Yes, a lot of times you can look at it as kind of modern day astrology as to kind of predicting the future based on what's happening from the stars, and certainly many cultures have done this in the past, and as you're mentioning, certainly that was done in Mesopotamia, and kind of getting readings from what these are telling the people at the time.
Now, black iron of heaven brought from the black iron of heaven, they brought from heaven. Right. They understood this in Anatolia. Now we come to a mystery that you introduce and cannot solve. Why are there so few samples given the ancient nature of China and its ability to keep records? You say that we have thousands of samples of asteroids in the US, and we haven't been here that long. The Chinese have been there 5,000 years or more. And you say, what, we only have 250 samples? Where are they?
That's a great question, and it sounds like a bit of a joke, but a lot of people believe, and there's some serious scientific evidence for this, that people in China were actually ingesting these meteorites. So when they would fall, they would be looked at as good luck or something like this, and the reason why we don't have many samples from China might be due to because there was a lot of eating of meteorites, and that may not be easy to think about, but you can grind it up and put it in a soup, I guess.
Now, all meteors are not iron. There are other. They look like rock, and we will speak of what they're made of. But I want to go now to the doubters, the denialism. It begins with the Greeks and the Romans. For heaven's sakes, it took men as accomplished as Aristotle all the way to Newton to deny this. But the stone that is most striking is the stone of Agostopotame, and you note the Greek Diogenes recognizes it. He knows that it's fallen from heaven. And later on, they claim, where does Aristotle claim these rocks come from? If not,
yeah, it's funny. We kind of knew what was happening. We knew rocks were falling from the heavens or from the skies, at the point of Diogenes. And then Aristotle comes along, one of the smartest guys around, and he changes everyone's mind. And the reason for that is because basically, in his mind, the heavens were perfect, and you didn't have room for these, kind of things that don't fit, and all these meteors and meteorites that are falling didn't fit with the perfection of the heavens, and so he just kind of cast them aside as not being real, or just like you said, folklore.
Yes, and that continues for 2,000 years. That's why we started with 1803. Aristotle, very influential. We do mention that Buddhism notes meteorites. The Inuit of Greenland note meteorites, or a 35-ton meteorite at Cape York. Buddhism notes meteorites. There's a very large crater on the Siberian-Mongolian border. So these objects have been falling for thousands of years. People have reacted to them with superstition, with admiration. There was a Roman emperor in the 3rd century AD, Common Era, who was quite clearly a rival for Caligula and conducted himself outrageously on the basis of a rock that fell from heaven. Some of these very famous rocks have disappeared. Does that mean we might be able to find them someday, Greg, or do we think they were pulverized?
Well, it would be great if we found some of them, particularly some of these interesting rocks that you hear about in history. But I guess I don't have a lot of hope. I feel like, humanity likes to pillage things and destroy things, unfortunately, and sometimes it's difficult to imagine destroying a large piece of iron or something like this, but it gets cut up, it gets spread around, and then it gets forgotten by history.
And in one instance, I believe the Christians destroyed a rock that was available. However, we come to what we do have. You have you have some of the rock that fell in Japan. You have some of the rock that fell in, what is this now, Siberia, and you begin to assemble what it looks like a museum collection of rocks. Do you still have them today to study?
Yeah, the community has an impressive amount of material available to it, and it's really impressive. I mean, unfortunately, we don't have all the meteorites that have ever fallen over history, but we have an incredible amount. I think it's something on the order of 50,000 different individual samples at this point.
In
that the community has.
1794 at Sienna, Italy, I wanted to mention this particularly because Italy is a wonderful, wonderful place, and Sienna is one of the magical cities of the world. Ambrogio Soldani writes a document on a shower of stones on the 16th of June. Now, that didn't persuade everybody, but it's what you say are the building blocks of Biot's revelation a decade later. So there were individuals who were recognizing that these things did not come from Vesuvius or did not come from the earth. Is that correct, Greg?
Yeah, that's correct. I mean, we had a large group of people that were kind of trying to figure out what was going on. And there were, many discussions and conferences and things about why are these rocks falling from the sky. They've continued to happen, since the planet was formed, of course, and certain stones that happened at the right time and the right place were very influential. And as you mentioned, Sienna was one of these falls because a lot of people in academics saw it. It was difficult to cast aside as just some farmer trying to make a name for himself. So this is a very important fall, yes.
All right, we've now established that America and meteorite study are the same age. We're now going to go forward with what meteorites coming from the asteroid belt, what they tell us about the formation of our solar system. The book is Impact, How Rocks from Space Led to Life, Culture, and Donkey Kong. Greg Brennecka is the author. Reasoning backwards, like a detective. No, as a detective, Greg is going to take us to the asteroid belt and what the asteroid belt and other objects in our solar system called planets, not all of them are planets, but it's important to mention that the building blocks of planets are everywhere. What they tell us about the formation of our solar system. So far, Greg, my understanding is the planets have moved. Why is the asteroid belt where it is after Mars? What does it represent?
That's a great question. And you're right. The planets have moved over the course of history of the solar system, and particularly the large planets, Jupiter and Saturn. They encompass a huge amount of mass in our solar system that's out, not in part of the sun. And their kind of gravitational interactions with the sun are what cause things to kind of move around because they're so large and they play such an important role. And the reason the asteroid belt is where it is because of this movement of the planets. There are different resonances, basically kind of zones that are gravitationally, well set up to be. And that's one of the zones where a lot of the sweepings from the asteroid or sweepings from the solar system ended up in that asteroid belt.
And the asteroid belt is the origin of many of these rocks that fall on Earth, and not entirely, but many of them. And they're very large asteroids, and then they're small asteroids. And I understand there have been collisions, and sometimes you can walk the cat backwards to where the collision took place. There was a NASA probe to Ceres and Vesta. Is that the other one?
Yep.
And are those planetesimals or large asteroids? There are many words for them. Are they the origins of some of our meteors? Have we linked things that fall to Earth from those large asteroids?
Yeah, particularly Vesta. We're able to kind of match what we know Vesta is made of from spectral lines using these probes that we send up and ground-based telescopes to samples we have on the ground that we can look at in the lab. And there's a pretty good match. And so we believe a lot of these samples, or at least one group of these samples, has come from Vesta. And we've done this with things like Mars as well, the moon, and we can kind of figure out where some of these meteorites are coming from, at least which bodies they're coming from.
You mentioned Mars. We have several rovers on the surface of Mars. Two of them are sleeping, Oppie and Spirit. Two of them from NASA are very active, Percy and Curiosity. The Chinese have a rover, Zhurong. We have many missions planned there. You have pieces of Mars now. What have we learned from the meteors first of all, how did they get here? What have we learned from them?
Well, they get here by impacts, actually. So you have, rocks that are floating around space and they hit Mars, and then they kick off pieces of Mars that end up flying to Earth. And we just kind of get lucky enough to get in the way. So that's how we have pieces of Mars, which is great because we haven't brought back samples yet, and hopefully will soon. But that's how we have pieces of Mars in our collection.
And you can identify Mars from other ejecta that comes our way, you can say this is clearly Mars. Your ability to discern the chemistry and the isotopes of an asteroid?
Yes, exactly. And one of the main ways that we've done this is due to some of these probes that we've sent up. For example, we were able to measure the atmospheric gases of Mars in the 1970s. And because we knew what the atmospheric gases were like, we saw some of these kind of weird meteorites that didn't fit in with other classes. The gases were measured in these, and they matched exactly with what was found in the Martian atmosphere. So that was kind of the, silver bullet, I guess, to tell us those samples are actually from Mars. So there's a lot of different chemical and isotopic signatures. That was one of the main ones.
Do we have pieces of the moon here? Do your meteorite collection identify not only the moon, but what side of the moon? The face of the moon is quite different than the backside.
Yes, so obviously we have a lot of samples that were collected in the Apollo and Luna missions. And we have, I think it's something like 300 meteorites that are also from the moon. And obviously with the Apollo samples, we know exactly where they're collected and it's well documented. Unfortunately for the meteorite samples, we know they're from the moon, but we don't necessarily know where from the moon they are. So we definitely do have samples from different parts of the moon, but it's just unclear as to where exactly.
I learned from you that the moon is an important metric when it was born or created or resulted from. The story I have, Greg, help me here, because it's been a few years since I read it, is that a Mars-sized planet collided or brushed alongside the Earth very early in the solar system and turned both objects into molten, Earth and what was left of the Mars-sized planet, unless the moon is made up of reconstituted everything, a little of this and a little of that. And the reason that's important is not because it's speculation, but because at that point, you report that it is hard to believe that there would be anything credible that could become organic on the Earth because of the heat. Is that correct?
Yeah, and you summarized it very, very nicely about, kind of how we think the moon was born, basically with that large impact. And yeah, when you have a flash melting of an entire planet, if life was here prior to that, it would be extinguished. It's just too hot. The temperature is just too great for anything organic to stick together. So it would be totally sterilized at that point. So you can speculate whether life existed or not before then. I think it's a pretty safe bet to say during that event and just after it, no life on Earth existed.
And that is where we now turn to analyzing what we have of meteors that have fallen to Earth, what we have of samples that we've returned from the moon, what we look forward to for samples from other planets, for example, Venus and other moons, what it tells us about the origins of everything: water, organic, complex organic molecules. The word life is too inarticulate. I'm just going to say we have building blocks that are everywhere. And when we come back, how is it that Greg and his colleagues do their job with the instrumentation available to them today? The book is Impact: How Rocks from Space Led to Life, Culture, and Donkey Kong. Greg Brennecka is the author. You teach me there are 3 kinds of meteorites that fall to Earth, our classifications. What are they? And you study one particular kind of meteorite, I believe, the CAIs. What is that? First, the 3 kinds.
Okay. Well, I guess I'll have to slightly correct you. There's a lot more than 3 kinds. I think there's 3 main kinds of chondrites. So I'll just kind of break it up into that. There are chondrites, which are really primitive samples, and then there are achondrites, which have melted. There are 3 types of chondrites. And one of those, you mentioned the CAIs, or calcium aluminum rich inclusions, and you can see why we abbreviate it. That's something that's contained in these carbonaceous chondrites, and they're kind of the earliest snapshots of our solar system. So as it was just starting to form.
So the chondrites are important because they are a journey back to the 4 billion years ago, when the cloud was gathering itself around what becomes the sun. That's why they're so important.
That's exactly right. They're very primitive samples. These chondrites are so important because they've never been melted. They really represent a snapshot of that molecular cloud, and kind of as planets and planetesimals were starting to form, the very Very beginning, the baby book of our solar system are contained, I guess, within these chondrites. Yeah.
All right, the three kinds of chondrites, and there are other kinds of asteroids, stony iron, just stony, achondrites, which has to do with whether the substance inside, test me, teacher, has melted or not. And chondrites are unmelted. Is that correct?
That is exactly correct. Chondrites are not melted, and achondrites are melted. It sounds, like we're really boring at naming things.
Well, but melting means that there's very little water present, or no water at all, because it's been put in a microwave in some fashion.
Yeah, there's a lot less water in these the rocks that have melted. Sure.
Now, I'm interested. The ordinary chondrite seems, not very compelling, but inside these chondrites, you can, again, teacher, help me. You can identify which side of the snow line they come from. What is the snow line?
So the snow line is something that people who study different planetary systems look at to kind of see what temperature water can exist. And it basically changes on the brightness, activity of the sun, the temperatures involved in the system. But it's basically when water can exist and when it's kind of too hot. Water ice, I guess I should say. So beyond the snow line, there's a lot of ice and water, whereas interior to the snow line, there's a lot less water.
1, 2, and 3 is the wettest. 4, 5, and 6 is the unwettest. Now, I understand you've broken these down. It's very helpful because we're looking for secrets within, and we're going to go inside these meteorites. But I want to pause at the calcium aluminum rich inclusion. You lost me, Greg. What does that mean? This is your specialty.
It is my specialty. I love them. They're great. Well, as you can probably guess based on their title, they have a lot of calcium and they have a lot of aluminum in them, and they're an inclusion. So it kind of tells you what it is right there. So they're little bits that are found within these very primitive meteorites. And what's cool about these CAIs, as we call them for short, is that they really are that first snapshot of the solar system. They are what we date to say how old the solar system is. So when somebody says the solar system's 4.567 billion years old, the way we get that is by dating these CAIs. And I've spent a lot of my career studying these CAIs, and I could talk for days about them, but I don't want to bore everyone.
Well, it's not boring. It's because what you've identified is a clock inside some meteorites, not all.
Yes. So because some samples have been melted post formation and things like this, they don't represent the most pristine samples. These CAIs generally are considered the first things that formed, and the clocks, isotopic clocks that exists within those are very valuable for us to understand, what was going on and when, and also what materials were making up the solar system, because that was changing early on. There's a collapsing gas cloud that is forming our solar system, and we see that change in these CAIs and then the things that formed after them. So it tells us a lot about how our solar system form and how stellar systems form in general.
The Enstatite, that's what a CAI is, an Enstatite. But there are other kinds of Enstatite. What does Enstatite mean?
Enstatite is just it's a mineral, essentially. It's just a designation of a grouping of elements. So Enstatite, certain chondrites have a lot of enstatite in them, and that's just why they're called enstatite chondrites. So enstatite is just a mineral that exists in very early form solids.
I understand. Now we go to the non-chondrite meteorites, and they are called, quite logically, achondrite because they've been melted. But what can we learn from them? Because at one point I wrote a note down saying some of these come from planets or disrupted planets. Is that how to think of them?
Exactly. Yeah. So because these are achondrites without chondrules, they basically have been melted, and the chondrules have probably been melted away. And when you have a large body that melts, you end up what we call differentiating, so that the iron goes to the core, much like in our Earth, much like in Mars. In large planets, the iron and associated elements will go to the core, and everything else kind of stays, near the surface or the crust. So these samples include samples of cores of planets that we don't have access to any other way. So a disrupted planet, you can get a piece of its core, and we, that gives us an opportunity to study the core of a planet, which we cannot do on Earth.
Those black iron that were noted by the ancients, are they achondrites? And did they come from planets?
Likely so. So it's hard to know without having the actual samples in hand. but likely they were using some of these large pieces of iron or iron-rich materials for their building materials, as is written in the text. And yeah, like I said, it's the only way that they could have made iron or they couldn't make iron at the time. It was the only way they had iron.
So you're like a forensic scientist. You're pulling apart rocks and telling us about where we came from and what other planets might look like, because we haven't traveled to them yet. Early days. Now, pallasite, that's named for Peter Pallas, who was one of the men who advanced the understanding of meteorites. What is a pallasite?
A pallacite is a really spectacularly gorgeous meteorite. It's what we think of as kind of like the core mantle boundary on Earth. So,
oh, this is the one that has green in it.
Yes, there's really these spectacular olivine crystals that are kind of entrapped within a big iron matrix. So it's this really spectacular sample. You cut it really thin and you can shine it up to the light, and it just looks absolutely unworldly, which I guess, pun intended. But yeah, they're really spectacular samples, and they're very robust samples. So we have quite a few of them that have survived the fall to Earth.
Now, how does Greg do all this work? He also gives us an appendix. You know a book by its appendix about how people have worked with meteorites since they were first recognized as coming from space. There was originally chemistry, and we mentioned Edward Howard. However, and you are a cosmochemist, but you have really fancy equipment, electron microscopes, but even those are discerned between a scanner and a transmission to electrodonoscope. This is all in the appendix. And then he takes me deeper and deeper. It's kind of like descending into other galaxies. We go to isotopic breakdown, something called a secondary iron mass spectrometry. All of this, is this within the last few years, Greg? How long has this been available?
These have developed over time, of course, but a lot of this machinery got started with the kind of excitement that surrounded the return of Apollo samples. So the race for the moon basically inspired a lot of people for a lot of reasons, some of them political, some of them scientific. But the outcome of that was that people really got interested in space and studying things from space. And it's largely because of that race for the moon that we have a lot of these interesting machines that exist now and really help us answer a lot of questions, not just with space science, but with pretty much anything we do in science. These are really important types of machines that are just groundbreaking.
You are the cosmochemist. What is solution chemistry?
That's when you dissolve your sample in acid generally. So you kind of disaggregate it and turn it into a solution. So then you can measure the elements and isotopics really, really well. You can do it without dissolving it, but it doesn't work quite as well.
So you must destroy the village to save it. I understand.
Exactly.
But
yes.
at the same time, that allows you to be very specific about, specific isn't adequate here. Like a detective, you can go to the scene of the event itself. How detailed can you get? Can you say when something left when it left Ceres, or when it left Mars? Can you do that?
We can actually. There's a lot of really cool, not just machines, but chemical procedures that allow us to separate certain elements that we really care about that will tell a story like that, usually in their isotopes. And because we're able to turn it into a solution by dissolving it, then we can basically manipulate it and get just that one chemical element that we care about out. And then it's basically a very clear signal that we can put into our machines, and it's not interfered with by other elements. So that's why we have to dissolve some of these samples. And luckily, John, I just want to say we don't have to dissolve very much of it. So it's not like we're dissolving the entire sample size of a basketball or anything. It's just a tiny fraction of it.
Well, these are big pieces of rock. I understand. Now, I want to note, before we go to the mystery of compound organic molecules, the funding for meteorite study. You mentioned the European European Research Council, JAXA, which is the Japanese Space Agency, much involved in the 2 Hayabusa missions, and NASA. And the funding looks adequate. Is that correct, Greg?
I would say that we could use more. It's kind of crazy to think about. I make the analogy in the book about what the total amount of funding per year that goes to planetary sciences, and it's not much. And if you look at like some of the Marvel origin stories, they're 10 times what we spend on trying to understand our own origin story. And I find that to be an interesting way of looking at it. About if you want to know what Wolverine's origin story is, then you're willing to spend $100 million. But to figure out humanity's origin story, well, we don't get quite as much.
All right, the big questions: where did water come from, and where did life come from? When we come back, Impact is the book. How Rocks from Space Led to Life, Culture, and Donkey Kong. Greg Brennecka is the author. Right now, Greg, I need a definition. What is a complex organic molecule?
Well, a complex organic molecule is a molecule that contains carbon, usually some hydrogen bonded to it. And then when it becomes complex, I guess it gets a little bigger than just carbon and hydrogen. So, the definition is quite fuzzy about what complex means, but it just means something that's got a little bit more to it than just carbon and hydrogen, I guess.
And the reason we're looking at them is because the word organic is highly suggestive. However, we don't have at this point, we don't have the formula that we need to put together organic molecules, amino acids, and meteorites. But it would appear that you have the elements for it. That's from reading your reporting. You don't go any farther than that. You just say that you have these elements, which is why the question is, were they here on Earth when the Earth was built? Or did they come from meteorites? But Greg, you've taught me that Earth and Mars and the asteroid belt and the meteorites that fall upon us, and even the comets that come in from the Oort cloud, we're all made of the same thing. Is that correct?
Essentially, yeah. So, different elements are going to be concentrated in different areas. But yeah, we're all kind of made from the same blended material from the molecular cloud. So yeah, you're right. We're all kind of the same stuff as just in different ratios.
So I have the page from Greg's book where he gives us a chart of present in meteorites, amino acids, nucleotides, and other selected essential molecules for life. This is a pretty long list, and you say that it could be a lot longer, and you're working on it all the time. So where are we going with this? We have rock, heated rock. This is the Earth recovering from the collision with the Mars-like planet. And we have, all right, let's veer away from that pursuit to go for water. Where does water come from? We can presume there wasn't much left after that collision.
That could be true. There's actually some evidence to suggest that water may have existed prior to that and then was maybe liberated during that moon forming impact and then basically settled back on the planet afterwards. So water doesn't necessarily have to be delivered from, the Oort cloud or from beyond Jupiter's orbit or anything like that. Earth has, what we think of as a lot of water on it, but that's only because it's on its surface. Earth doesn't actually have that much water on it when you compare it to other meteorites or other samples in the solar system like meteorites.
The reason I ask after water is because I understand we need three. I've been taught you need three elements for life. You need water, you need energy, and you need rock. Okay, so we have rock on Earth. We have plenty of energy. The core is, we have a volcanic, we're geologically active. We also have the sun. And we have two elements and we have lots of rock. So meteorites, what do they tell us about organic molecules being introduced into Earth with impact? And if they're part of the solar system, does that mean this is a pursuit that you will continue throughout the solar system when we have more samples?
So yeah, I think you're right. We need all those things for life to exist and get kickstarted. But you need kind of you need amino acids. You need kind of what we're made of, or DNA, things like that. And how that assembles is certainly not something I have the answer to. But I think what's interesting is that we have all of those ingredients that are present in meteorites, and they were delivered to the early Earth. So I think that's what I found to be the most interesting when learning about this in graduate school and since studying it, is that all of these things exist and are created. Amino acids, they exist and they're created in the outer solar system, and then of course when they're delivered to planets like Earth, then they provide ingredients for life to get kickstarted. So I'm not saying that meteorites brought life to Earth. I'm saying they brought the ingredients that allowed life to get started.
Right. And the nucleotides are, you have the list here: adenine, guanine, and uracil. Two of them have DNA and RNA in them. One of them is just RNA. But I read speculation all the time. I get Science Magazine and Nature Magazine. I have no idea what's going on, but I enjoy reading titles that I can't solve. And I see routinely they're keen on RNA these days, very keen. Are you, as a cosmochemist, looking at meteorites, are you keen on RNA as well?
I'm keen on RNA. I'm keen on DNA. I like all the amino acids. I like all the nucleotide bases. I'm non-discriminatory with that, I guess.
And why are you pursuing them? Is because is it reasoned that that's part of the missing formula, how that happens to come together with something that moves?
I think the kind of difficulty for life to get started on Earth is made a lot easier when you are delivered kind of pre-made sets of things like nucleotide bases and amino acids. If you only start with elements and they're not already kind of put together, then the emergence of life becomes very, very difficult problem to solve. Whereas if you're kind of delivered a ready to go kit of amino acids and parts of DNA, then life getting kickstarted becomes a lot easier, I guess is kind of how I see it.
All right, Professor. I give you a test that I enjoy giving to people who are working at the frontier of the known, which is what you're doing. I give you an unlimited budget. What do you do next, Greg? We have a couple of minutes. You can spend money.
Okay, well, I think what I will say, what we're doing right now is fantastic in the space missions that are bringing samples back. An unlimited budget just to look at meteorites is not necessarily incredibly helpful, because those meteorites came from an area that's more pristine in outer space. I think what's going on with samples coming back from Bennu and Ryugu in these sample return missions is exactly what I would want to do, because it allows us to go out and get samples of asteroids that are very, very pristine, that really are the first snapshots of when planetary bodies started to form. And we've already found that amino acids exist in these types of meteorites that have never been on Earth's surface. So it's not like it could be contaminated. These things are in outer space. To take to your question about unlimited budget, I think doing exactly what we're doing with space missions, going to collect samples from Mars, going to asteroids to get samples, this really helps us figure out how everything got going and continues to thrive.
So mounting a mission to the asteroid belt would be in train. Mounting a mission to any of the moons of Jupiter or Saturn would be in train. That's about to happen. Mounting missions to the surface of Venus would help if you get a sample back, if that's possible. All of that, you're just collecting more and more evidence and pursuing the question of how we got here.
Yeah, I mean, our origins are really interesting to a lot of people. Whether you're a philosopher, a religious leader, if you're a scientist, it doesn't really matter. People look backwards to find out where we came from. And this is the way to do it from a scientific perspective, is to study meteorites, to study the early solar system. So that's at least my perspective of it.
The book is Impact: How Rocks from Space Led to Life, Culture, and Donkey Kong. Greg Brennecka is the author. This is CBS Eye on the World. I'm John Batchelor.